आ गई।
अब अपना खोलो, जूम खोलो, जूम।
Okay, बच्चों, am I audible to all of you? Dinesh, am I audible, beta? Let us figure out a new topic after the reflection, that is the refraction of a light. Till now, we have talked about when the ray of a light was propagating from one medium and it was remained in that medium only, right?
Keep yourself as talking. Keep only active speaker on mode bus बना लो. Keep only active speaker mode as you.
Okay, so we are going to talk about refraction part. In the refraction part, what we have is
नीचे लाओ, ये देखो. नीचे खींचो उसको. ठीक है.
the ray of a light. If we talk about reflection part, the ray of a light was traveling from one medium only and it was remained in that medium only. I hope I am audible to everyone. Yes or no? Okay, बच्चों, this is live streaming on YouTube as well. If you wanted to figure it out, you can figure it out from the YouTube channel, that is Triple A Physics, AAA Physics, Triple A Physics. This is my channel name, and I have uploaded the reflection part and the class 9th, and within few days we are going to upload the 11th part as well. Okay, so biology section also is there in a collaboration with one of the experienced faculty. So Dr. Abhishek Singh, this is the name of the faculty. He is in collaboration with us. Now let us start the topic, the refraction part. So in refraction, till now we have studied about reflection. I already told you a ray of a light traveling from one medium and remained in that same medium. That is what the reflection part we did. After every reflection, what we saw that the velocity of the light remains the same, but the intensity of the energy gradually reduces after every reflection. This is what we have seen in the reflection part. Now we are going to talk about refraction. So for understanding the refraction part, the phenomena of refraction, when the light of a mm, this the light travels from one medium to another medium. This is the velocity v1 of the ray of a light. When we say ray of a light, it means we are talking about monochromatic light. Okay, so we are not talking about the combination of the Vibgyor, that is white light. We are talking about the single monochromatic light. So that particular light has some frequency, some amplitude, means it has some wave nature, and few of the parameters of that particular electromagnetic wave, to which we say light, few of the parameters changes and few of the parameters are remained constant. So we have to be very careful and we have to understand those as well. When a ray of a light travels from one medium to another medium, we only understand that the light traveling from one medium to another medium simply changes its direction from the initial direction, but it is not a true statement. This is only not the phenomena defining the refraction. There are few other phenomena as well. So for that, let us calculate the wave nature as well. So if we talk about the wave nature of a monochromatic light. So first is speed. We have, what is the speed? Speed is v is equal to nu lambda, where nu is, what is nu? Any one of you? Nu is frequency, right? Now what is lambda? Lambda is the wavelength. Wavelength. So we need to see other parameters as well. Amplitude. Amplitude is the distance which defines the maximum disturbance from its mean. If this is the mean, this is the amplitude we will talk about. This is the negative side of the amplitude. Okay. As we have already done this topic, so we are just having a recap of this. Now, frequency. What is frequency? If I talk about frequency, frequency is not a physical existing term like speed, velocity. These are not physically existing term, but the distance is a physical existing term. So for our convenience to understand the relative parameter, how much slow or how much fast a body, an object, a particle is, we take the help of speed. On that same ground, we take the help of frequency for the simplification of our study of any wave. What is frequency? Frequency is, we do not bother what direction the propagation of the wave is, what kind of wave it is. We simply talk about number of disturbance or number of oscillations created. Number of oscillations created in 1 second. This is what we have fixed the time, as we fixed in speed in a unit time. How much is the distance or displacement traveled? That too we talk about the term velocity and speed. So on the same ground, while fixing the time 1 second, here we do not say unit time. We specify the time magnitude as well, as that is 1 second. In 1 second, we talk about how much is the amount of oscillations. That too we say frequency. So number of oscillation in 1 second. This is what we talk about frequency, denoted by the word nu. Now again, so these are the parameters which we have talked about. Now wavelength. And one thing, we should be very precise and careful, that frequency is dependent of any of the wave. It depends on the source. The source who produced the wave, the frequency depends on that. Suppose we have a light ray, and the light is coming from the sun. So sun is the creator, and whatever the frequency is of that particular white light, when it propagates from vacuum to air, air to water, water to glass, again to air, or other optical denser mediums, we have the frequency always constant. The term, many of the term changes, but the frequency is constant. Now if I talk about wavelength, for the understanding of wavelength, suppose you are in a classroom and there is a gallery. Now in the gallery, the gallery is approximately 50 meter we are taking. 50 meter a gallery is. Now two students are standing there. Now I tell you to walk from the gallery from 0 meter to 100 meter, you have to walk. So you start walking while taking your one step a very longer distance, as much as your 2 feet can do. So that too you travel in a very less time, as compared to if the 100 number of students are standing in that same uh, gallery, which is very narrow gallery, and 100 students in entire 150 meter of length, the students are standing. Now what you will do, you will shorter your wavelength, because if you because you cannot have step a very long step, because the collision will be there maximum. That is what the 100 students are actually defining the optical density of the particular medium. And you have shorter your wavelength, because one thing is fixed, that you needed to go from one point to another point. That is what you have to propagate the wave. So ultimately what you will do, you will shorter your number of steps. This number of step is only the wavelength. When the ray of a light travels from one medium to another medium, it shorter its steps, it shorter its wavelength to propagate from one medium to another medium. As a result, when the wavelength shorter itself, try to see this formula, velocity is equal to nu lambda. If the lambda is shorted, as this is a constant, equals to and constant and combination will tell you that velocity is directly proportional to wavelength. If wavelength is shorted, then the velocity will also be shorter. So velocity in an optical denser medium always reduces itself, because the reason is the wavelength reduces itself due to increase in optical density. So we needed to understand the term optical density as well. As we have gone through the first of all, let us see the wavelength part and then we will move further. This is the wave we have, and in this wave, if I talk about your books, in your book it is written from crest to crest, trough to trough. That is a the distance measured. That is only the wavelength. No, that is not actually the situation. The situation is any point on a wave with a another conjugative point next to the wave at same phase. That is known as that distance is known as wavelength. Let me show you. If you're taking this point, so at the same phase, if you talk about the same point, this that is what the wavelength is. From crest to crest, trough to trough, that is also a wavelength only, but only from crest to crest and trough to trough, that cannot be said to be a wavelength, because wavelength is a term from one phase to the same phase in the next wave we have. That length is actually the wavelength. So you have to be very careful when you talk about the wavelength. So this will be the next at the same phase. This is what the wavelength we have. So wavelength we have talked about. We have talked about frequency, amplitude, speed. Basic terms we are clear with. We should understand the term. Now let us talk about the optical density. So, what is optical density? To understand that, we have one of the comparing parameter, and that comparing parameter is known as refractive index. Index is the actually term of ratio. Index is actually the term of ratio of of the same physical quantities. So, refractive index we are going to talk about, which is symbolized by mu. Okay, so what is refractive index? As I told you, when a ray of a light travels from one medium to another medium, this is a ray of a light, this is the point of incident, this is the incident ray, and it is having some velocity v1s. Now, at the point of incident, this is what we know, if this is medium 1 and this is medium 2. So, this line which divides the two mediums optical density, that is known as interface. Now, at point of incident, we see the normal. Why we see the normal? Because normal is the reference for the measurement of angle. All the angles of incident, reflection, refraction, all are measured from the reference of normal only. So this is the value of incident angle, and this is the actual path. If there is no change in the medium, then this is the actual path of the incident ray. But the incident ray, due to the change in refractive, suppose this is the mu1 refractive index of medium 1 with respect to vacuum. This is absolute refractive index of a medium, and this is the medium 2, and we assume that medium 2 has more optical density than 1. So in that case, we found a special behavior of the ray of a light, that is, it travels such that it bends from initial path towards the normal, and the amount is bending is represented by eta, and this eta represents the angle of deviation. This is what we have, angle of deviation. Now this angle from the normal reference, as I told you, incident, reflected, refracted, all are from the reference of normal only. So this is what angle of refraction. So this is what the basic story we are talking about. when the ray of a light travels from one medium to another. Now this is traveling in medium number 2, and the velocity here is v2. So we have a few terms to define the refractive index. The first term we talk about wavelength and change in velocity. As per that only we can say, if I say mu2 with respect to 1, then we will say, because it is an index ratio, directly we will say we are talking about mu2 with respect to 1. We can write in these pattern as well. Mu2 1, as I already have written, you can write mu2 1 this way as well. Mu2 1, mu2 1. These are the pattern, but generally students use this kind of pattern of defining the relative refractive index. This is absolute refractive index mu, which is taken from the reference of vacuum or free space. Now this is what relative refractive index. Relative refractive index. Okay. So let us talk about mu2 with respect to 1. So we are talking about mu2 with respect to 1. So mu2 with respect to 1. I hope you all are understanding. When we were talking about in the previous classes, we have talked about the relation of relative density. We were taking the relative density that we were taking the relative density. From where we were taking the relative density? We were taking the relative density from the reference of water at 4 degrees Celsius. On same ground, we are going to talk about the term, the term of, the term of, any one of you, the term of optical denser medium with respect to the reference which we are taking. This is one of the formula, and the another will be when the light travels from one medium to another medium, it observes, we observe some of the changement that too we are talking about. So initially the velocity was v1 divided by v2. Always remember this term. Absolute refractive index of 1 is actually velocity of light in vacuum divided by velocity of the light in that particular medium. I needed the refractive index of any medium, its velocity will be written in denominator, and the numerator part, the velocity of the maximum velocity is written, that is velocity in vacuum. Okay, so here if we are talking about refractive index of 1, refractive index of 2 with respect to 1. So in that case, the refractive index we are talking 2, so we will write the velocity of 2 in the denominator part always. You can see this formula. If I talk about mu2, mu2 can be written as velocity in vacuum divided by velocity into divided by, if we talk about this, velocity in vacuum divided by velocity in 1. Now we can see these two numerator parts are cancelled out, and we are remained with the term of v1 upon v2. So if we are talking about a refractive index, then that velocity will be in the denominator part. So this is the conclusion we have with respect to velocity. Now, for better understanding of the refractive index with other parameter as well, we have another parameter that it gets deviated as well. So for that, let us figure it out what the situation is. I'm sorry. For that, we have the angle of incident and angle of refraction relation. Let us figure it out how the terms changes. There was a scientist named Snail. He did few of the observation. Let us figure out those observation to tell what is refractive index. So Snell's law, Snell's law. So this is our interface which changes the medium from medium 1 to medium 2, and from this interface any of the light ray we have, this is the point of incident, Then we have a normal. This is the normal at this location of points of incident. And then we have the refracted ray. This is what we have, the refracted ray. This is the real incident path as well. If the medium does not change, this would be the path. This is the deviation faced by the refracted ray. So this is mu 2, this is mu 1, this is the angle of deviation, this is angle of refraction. So these are the parameters we have. This is the angle of incident from the normal. Now we can see that this normal, if I produce this normal, or if I see this normal is making a right triangle. This is the normal right 90-degree angle, and this is the incident angle. Again, if I see this part, this is also making a right triangle. So this is what the situation we have, and in this situation we can see that these sides ratio and these normal ratios are same, and one of the angle is also same. So we get the number of points to identify these two triangles as a similar triangle. If the angles are similar, it means their ratios of angle will be always same, because ratio of sides are same, therefore the ratio of angle will be same. So for that, the Snail's law introduced these angles term, and for introducing this angle terms in the ratio of the sides, we use the trigonometrical function as sine angle. And he introduced the term that a sine of angle of I is directly proportional to sine of angle of R, which means the ratio of these two sine functions of angle will always be constant. This is what the Snail first defined in his theory part. So we can write this as sine I is equal to introducing the constant, and that constant was the medium. The medium's refractive index mu sine r. If we are talking about medium 1 and medium 2, so I'm going to write this is we are talking about mu 2 with respect to 1. So we have mu 2 1 is equal to sine I upon sine r. This is what the relation explained by Snail's law. Now, let us introduce more than two mediums and try to analyze what would be the angle of incident and angle of refraction in terms of relative densities as well. Okay, let us figure it out. We have, suppose this is one of the medium. Sir, you are muted. Now, am I audible, beta? I hope you all can hear me. My voice should be clean. Please pardon. Am I audible to all of you? Right? Bacho, am I audible? Hurry up. This is the incident ray. Can you all see this? Angle of incident. And this is the refract refracted ray we have. Then here the medium changes. Again the medium changes. This is medium 4, this is medium 1. And from this again the ray moves this way. Now let me tell you a interesting thing. If this is a medium 1 and the last one is medium 1 only, then in that case the emergent ray and the incident ray, they will be parallel. One thing, whatever the refraction part is going on in different mediums, but you will get that this is I angle, this is I am saying x1. If this is x1, then we can see that this is normal and this angle will be alternative angle because the two normals are parallel to each other. If the normals are parallel to each other, beta, I think I am audible to all of you. Yes or no? Srishti, can you hear me? Dinesh?
Sir, you are muted.
Now the voice is clear? Is my voice clear? Priyadarshan, beta, my voice is clear? Please tell, because you all are not audible to me. Dinesh, please write in chat. This is angle I only. Let me zoom this part so that it may be more clear to you all. I hope this is more clear now. Dinesh, please write in the chat if you wanted to say something. Right, beta? I'm asking that I am clean audible to all of you. If not, then please let me know in the chat. Now let us talk about the snail part, the snail's law, to which we were talking about. So in this part, sine of angle we are talking about. Sine I upon sine r defines the refractive index of the medium. For that, we have the term, we needed the refractive index mu of the medium 3 with respect to 2. Is it clear? Of the medium 3, this is medium 3 with respect to medium 2. So what I will write, mu 3 upon mu 2, this is one statement. But my mic is on. I think you all should listen my voice cleanly. Acha, do one thing. Just open this in my YouTube channel. Let me show you my YouTube channel. This is my YouTube channel in the name of Triple A Physics. Just open that, you will get to know. Hurry up. Can you hear it in that? Can you hear in the channel? Can you hear? This is the name Triple A Physics. You'll get to know. This is the channel. Is it clear? Hurry up and let me know. Dinesh, is it clear, beta? Now is it clear? Have you all open in that YouTube? Please let me know so that we may start again the part which I am telling you all. Okay, no issue, beta. If I'm audible on YouTube, just go ahead there only and just see the session. Okay, fine. And if any query,
Hello, sir.
just yeah, you are audible, beta. If any query, you write in the chat box in the YouTube part only. I'll attend that. Okay, don't worry. Is it clear? Just a moment. It is coming in the 3D view. Let me see the setting parts. But so in the YouTube, is it okay? In the YouTube, voice as well as the screen is okay. Please hurry up and let me know. Hey, beta. Okay, in YouTube it is clear, right? Please let me know. Please write in the chat box. Hurry up so that we may begin. Okay, great. Mu 3 and mu 2 we are talking about. Fine. So, in that case, we have the term. The term will be mu 3, mu 2. We have this general formula. I have written this. Now, let me write here. But if you will talk about Zoom, the voice is not coming as the student told me. But if you talk about the uh, YouTube, in YouTube it is coming. So please go there and you can watch. As I have the mic on in Zoom as well. I have the mic in Zoom as well on, but you all are not. Yeah, YouTube only. Yes. Okay. Let's back, and we are talking about relative refractive index. Mu 3 with respect to 2. Okay. So mu 3 with respect to 2, general formula I've written mu 3 upon mu 2. And in terms of velocity, you will be writing, we are talking about mu 3. So we will write v3 in downward in denominator, and this will be mu 2. This is what we have. One statement we are talking about with respect to velocities. Now, sine of angle of incident, sine of angle of refraction we are talking about. Which one will be the angle of incident and refraction? Now, we are talking about mu 3. Try to understand. We are talking about mu 3 with respect to 2. So, which angle? So, which is the interface between 2 and 3? If I talk about 2 and 3, this is the interface. So if this is the interface and I'm talking about mu 3, then it means that the incident would be coming from the mu 1, sorry, mu 2. So the incident angle will be considered as this angle, and this angle is actually x1. And if I talk about the refractive angle of refraction in the mu 3 part, that would be x2. This is what the term is. For more understanding, see this diagram as well. Angle of incident, angle of refraction. This is mu 1 or simply mu. This is I. So what you write, mu is equal to sine I upon sine R. So where is I? The I angle is at this vacuum, and this is the absolute refractive index, where the refracted angle would be fine. Okay, so now again I'm writing mu of 3 with respect to 4. Now again I've changed the situation, and the situation is totally adverse. If I talk about the situation, if I talk about the situation, hello, 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 mu 3 with respect to 4. So in mu 3 with respect to 4, what we are talking about, mu 3 upon mu 4 simply, then v4 upon v3, because we are talking about mu 3. So mu v3 will be in denominator. One statement. Now the another sine of angle we are talking about, sine I upon sine R we have to write. So angle of incident will be in the will be in the medium 4. Angle of refraction is always in that particular refractive index to which we are talking about. So we are talking about mu 3. So it means refracted angle will be in 3 medium. This is mu 3 4 interface. So this angle is the angle of refraction, because we are talking about mu 3 with respect to mu 4. Okay, this will be the refractive and this will be the incident for that particular case of mu 3 4. So for mu 3 4, this is the angle of refraction, that is x2, and x3 will be the angle of incident in that particular case. why I am taking these type of situations, so that you may better understand the terms which incident or which refraction you have to take into consideration when you are solving the questions. Okay. I know students in this part you are not getting my voice, but I am audible in YouTube. Okay, so please go ahead and check it out. I'm writing in the chat as well. Okay, now after this part, let us figure out the term after refraction. Let us figure out few other terms. There is a situation in which the number of students get confused, and that situation is there is an angle of incident, angle of refraction. Suppose I have taken that this medium 2 is a denser medium than medium 1. Medium 2 is denser and medium 1 is rarer. In that case, you will say, sir, the incident ray will bend towards the normal and we will get the refracted angle. So, this is the incident ray. Point of incident, then we will have a normal here, and this is what the refracted ray you will say. And you will found a wonderful and interesting thing that angle of incident is greater than angle of refraction. We never say that they two are equal. The two will be equal if the medium does not change, and the we will get the two straight line. This is normal, this is this way. So this angle is incident and this would be incident only because these are the vertical opposite angles. We very well know that this is the actual path of the incident ray. This is angle of deviation, and we have a equation angle of incident will be equal to angle of refraction plus angle of deviation. This is what the relation we also know. Now, one interesting thing I wanted to talk with you all, that sine I is directly proportional to sine r. If I start increasing this angle of incident, what will happen? The refracted angle will also increase itself. Okay, fine. Now, if I start reducing this angle from the normal reference, what will happen? Means this is the incident ray. This is I'm talking about. This is ray number 1. This is ray number 2. This is ray number 3. And gradually what we will get, the ray number 1 will be, and this is ray number 1. This is ray number 2. And this is ray number 3. And in every situation, the angle of refraction was less than that of angle of incident. Three part we have. But now I am reducing it more. What happens? There comes a situation that the incident angle is 0. And when the incident angle is 0, what we found an interesting thing. The interesting thing is that this is the ray, incident ray, and here only we have the normal. This is the normal as well. This is the normal and this is the reflected ray, which will go straight. Okay, so in this situation, we can say angle I is 0 and angle R refraction is 0. This is mu 2, this is mu 1, and if I talk about mu 2 with respect to 1, we have mu 2 upon mu 1, which is a non-zero value. Means we have some density, optical density of this medium 2 with respect to 1. It is not a zero value. But if I talk about as per the Snails law, many of the students are understanding that now the refractive index should be 0 as per that formula, that is sine I upon sine r, mu of 2 with respect to 1. So let me clear you a very mathematical term, that is sine I will be 0 and sine r the angle will be 0, which will give you 0 upon 0, which is undefined. What does it mean? It means undefined means the value may range from 0 to infinity, any of the value it would be. Mathematically, it cannot be defined as per this term. In that case, the Snail's law is limited to give you the value of refractive index. So in that particular case, we use the different terms because we have many terms of the finding the refractive index, as we have velocity v1 here, velocity v2 here. Again, if this is a mu1 only, so again we will have the velocity 1 only. So mu2 with respect to 1, we can write mu2 upon mu1 or v1 upon v2. The velocity ratios will give you the idea of refractive index in that particular case. When the ray is a normal and it directly moves, so it shows you that the incident angle and the refracted angles are 0. There would be no deviation in the ray, but still there is a refractive index, and you cannot say that refractive index is responsible for changing the direction of a propagating wave. So if there is no changement of the direction, it doesn't mean that the refractive index is 0. It simply means that this formula is limited for this specific case, and we can identify the refractive index by the velocities, by the speed of the light propagating, that is v1 and v2, and the ratio of v1 upon v2 will provide you the value. So this is what we are done with the Snail's law. We are done with the introduction of refractive index. We are done with the term of refraction phenomena. This is what we have talked about, the nature of light as well. Now let us talk about the part of the questions, the part of the concepts, as if refraction through a glass slab. Let us figure out what is glass slab. A cuboidal shape of a glass, and from which the ray propagates, that is what the glass slab. So we have the term of incident ray, and this incident ray is propagating from one medium as mu1. This is any medium mu2. Okay, you should have the understanding of this term. If even I'm not writing, then this ray gets refracted from the point of incident, and this is what the refracted ray we have. Okay, now again at this point, what we get is this is the emergent ray, and the angle here would be, this is the refracted angle. This will also be the same angle as this normal, and these two normals are parallel to each other. So we have the alternative angles among them, and these two angles are equal. This is the angle of incident, and this is the angle of emergent. We very well know if the two lines are parallel. This is the original path of the ray of light. This is the emergent ray, and they both are parallel in nature. They both are parallel. So, what actually this glass slab has done? If there would be no glass, then it would be propagating in this direction only, which I'm drawing right now. So, it has laterally shifted itself with a length of L. So, it is known as lateral displacement of the ray of a light. This is the emergent ray, and the angle of emergent is equal to the angle of incident only if we have a rectangular symmetrical glass slab. Okay, so the heading is rectangular glass slab. Refraction through a rectangular glass slab. Refraction through rectangular glass slab. Now let us see the bending of a light and the application part of this type of refraction. So for that we have the concept, and the concept is, suppose this is the beaker, and in this beaker the water is filled to this level. Now when the incident ray comes, this is the incident ray. Suppose I have an electric bulb inside this. This is the bulb, and the bulb is glowing. When the bulb glows, what happens? The incident light will pass all over, and we can see, we can take any of the random incident light ray. Suppose I'm taking this as an incident ray this way, and any of the random again I have taken. So these are the two random rays. One normal to the interface, it will be refracted and it will go straight only. After refraction, it will go straight. We very well know right now only Snails law we have defined. Now at this point of incident, medium is changing. Medium 2, this is medium 1. So we will have the normal, and we see that this is the angle of incident. And in this situation, the ray moves from the denser medium towards the rarer medium. In that situation, the whatever the initial path of the incident ray is, the ray will bend away from the normal. So it will go this way. This is what the refracted ray. Here the velocity is v2. Here the velocity of the ray of propagation is v1. In this situation, we can see that if our eye is placed here, if our eye is placed, then what we found the interesting part, that our eye receives this ray and this ray as well. When our eye receives something, what is the persistency of an eye? Just try to understand this part as well. As I told you in the reflection part, the same I'm going to tell you. Whatever our eye receives the light, it produces back in the straight line only. I'm not talking about a real track to be traced in the backward direction. I am talking about, even you can take the imaginary part as well, as we did in plane mirror reflection part. So the ray, whatever the light receives, light is being received by our eye. Our eye says from where this light is coming, and it retraces the path. But the condition is it always traces in the straight line only. It does not bend the ray of a light independent of the medium. It simply retraces the path by straight producing it back, and wherever it cuts, it always cuts virtually. If it cuts virtually, then definitely that is the location where we are getting the value of that particular location, where our eye is persisting the image of that object. So our eye says that that is the location of the object. So you can see this. If I retrace this in a straight path, I am getting somewhat this location. when you produce these two ray from your eye back, this is what the intersection I'm getting. So our eye will persist that me I am seeing the object at this location. But here is the object really here? No. This is the eye persistency which we are talking about. So this is our eye, actually this is our eye's persistency. So our eye says that here is the object, but that is actually the image. How it says? By reproducing the received ray in their back same path, and it produces those rays straight wherever first the two received ray intersects. That is what the location persists by your eye. So that is the location of your image, and the object we very well know actually the object is here. So o object, h image. Now we can say that this is the amount of height which is raised. So that is why we have the new depth. This is the new depth, h dash. So h dash is actually apparent depth. Apparent depth inside the water. So what you see inside the water, suppose you are at the bank of a river, you can see the stones, circular stones are there at the bank. So as you see the height, whatever you see the height of the stone from the surface of the water is not actually that, because you are seeing h dash at that situation. So actually it is in depth, and when you are putting your leg down, you can see that your leg gets immersed more as compared to what you were visualizing. So this is what the apparent depth we talked about, and this is the raise of height of the object as an image. So this is what the refraction we have talked about in the two mediums when the interface was horizontal. Okay. Now we will talk about when the interface is curved in the form of curve. So we are going to talk about lenses. So for lenses, we should know some parameters. Formation of lens. Formation of lens. Now if I talk about formation of the lens, uh, we should know what kind of lens we will talk about. There are many types of lens: spherical lens, cylindrical lens. If I talk about spherical lens, the word is very clear that sphere I'm talking about. This is the sphere. So from this sphere only, I'll make a lens. So that will be known as spherical lens. If I talk about the cylindrical, so this is what the cylinder we have, and from this cylinder we are going to make the lens, and that would be a cylindrical lens. Now for making a lens, what we do is we actually cut the part of this sphere. Suppose I cut the lens, I wanted to make the lens, I cut the entire part of the sphere this way, and this is the part I have taken out. This is the sphere, a complete sphere. Okay, 3D structure. Try to see me in the video, cam video. So this is the sphere. Now if I cut the part of the sphere from any of the chord, any of the chord, in that case, what will happen? In that case, what will happen? This is the sphere, and if I cut it randomly, not from the diameter, from anywhere, in that situation, what will happen? This is that I have shown you. Now this is the part, and this is the cutted part which you have. So if you view it from the side, you will see only this curve part. This is not the radius, any kind of radius. Sorry, any kind of part of the circle. No, this is not circle. This is actually the three-dimensional sphere part. So it will, if you view from this side, it will be in this shape. So this is what actually we are talking about. Let us see this cutted part. Now this is what the cutted part we have. This is what we the cutted part we have. Now these are the aperture, and this is the effective length. Aperture, effective length, many of the term are common from the reflection part which we were talking about. Here there we took a hollow spherical glass. Here we are taking a solid spherical glass. So this is the cutted part we have. This is one type of curvature at this side. Here the curvature is a plane part. So if I complete the sphere, it would be again this way. So this surface number 1 will have its center. If this is the diameter part, this will be the center, and this center is actually center of curvature, this point. Now, half of the length of this will give you the, this is the part. If this is the center of curvature, half of its length will give you the focus point, and this will be the focal length. This is the radius of this curvature, and this is the focal length. Now, for letting your confusion to be very clear, let me tell you, if this is the part, then in that case, we take the median of the material part or symmetry part as the optical center. So this is one of the part. Now we are cutting another part from another or from the same sphere only. Suppose I cut this part as well. This done, this part as well. So this will be the surface number 2 as this was surface number 1. So that will be joined with this will give you the bifocal lens. Bifocal means the two focus will be there, because we have two curvatures, S2, S1. In your syllabus part, S1 and S2 will be identical. They will have the same radius, same focus. I'm talking about till class 10th. If we talk about the class 12th optics part, in that ray optics part, we have the two different surfaces with the cutted from the different spheres of different radius of curvature, and different focal will be there. So R1, R2, F1, F2, like that the terms are there. In that case, we use mirror formula. So here, first of all, let us calculate this part in the nomenclature. This is the lens we have. I'm not drawing the line that this part. I will draw this in the dotted portion. So this is what the part. This is what the part we have. Now let me tell you few of the terms which you are familiar from your book. You all have seen as well. This is the principal axis, and this is the optical center we talk about. This is the actually the optical center, and this optical center passes straight. Now, if I have a ray of a light this way, whatever the ray with any angle from the principal axis, if it passes through the optical center, in mirror we were having pole. Now here we have optical center O, there P, here O. If it passes straight without bending. How is it possible? Because the refraction is going on. How is it possible to have this? Let me clear your confusion at this side. Let me draw a big diagram for you all. When the ray of incident comes to this point, this is the incident ray, and we have this surface. Now you very well know at this point where the incident point is there, from that point we will draw the normal. And if we will draw the normal at this point, what we will see, a interesting thing, that interesting thing is that this normal is going to cut. will cut at the center of curvature. So this is the normal. It will cut the center of curvature. This is the center of curvature. This is suppose the focus. So in this situation, what will happen? The incident ray, whatever the angle it is making, or angle of incident, it will make some angle of refraction. It will get refracted, no doubt. It will get refracted. After this point, as this point will come, what will happen? It will again get refracted, and it will, whatever the deviation it has phased from S1 surface, whatever the deviation of the ray due to refraction it has phased from this surface S1, the same it will phase the angle of deviation in opposite direction, and this ray will again come to parallel. So this is actually the refracted ray in the medium, in between the lens. That ray will deviate slightly, and it will become again parallel. And if the lens thickness is assumed to be very less, then this ray and parallel to this ray will assumed at coinciding, and that is actually the straight line. Again, I'm drawing that part with a very enlarged pattern. If this is the optical center and this is the ray passing, this is actually the situation. I'm enlarging it, micro size, you can say. We are talking in very detail. So ultimately, the conclusion of this we talk about: a ray of a light passing through this optical center will pass in a straight line. I hope I'm clear to everybody. If any query, please let me know in the comment box. Okay, I'll attend your queries there itself. Have you all understood this part? Just let me know, yes or no. Okay, great. Now we will talk about, now we have understood, if any ray is passing through a optical center, definitely it will have the straight path. Okay. This is one of the law we have actually talked about, when a ray of a light passes through a optical center of a bifocal spherical lens. This is one kind of nature of the lens we have talked about. Now let us talk about, this is first law of reflection, sorry, refraction. Law of refraction through convex lens. Now I have used the word convex, which is made by a spherical glass. So it is a spherical lens only, and the name is convex. How it is known as convex? Let us talk about that part. As I told you, this is a bifocal. So from the aperture point, these are the two aperture. This is ultimately the effective length. From the effective length, if the surface, the refracting surface, is bulged out, then that surface is actually the convex shape of surface. One thing. This is one part and this is another part, and we join together to get a bifocal convex length. This is another surface, refracting surface, which is bulged out from the effective length from the aperture. So that is why the name is convex lens. Try to note it down, these words, How to detect convex or concave, because it is very essential to understand. If I'll give you convex and by convex concavo, concave convexo type of lens, you won't be able to judge which kind of lens it would be. So for that, always remember the concept for which we talk about whether it would be a convex or a concave lens. Now next term, the next term is the second part of the law of refraction through spherical means convex lens. So in this part, what we are going to talk about, we are actually going to talk about the next law, that is the same as we talked about in the reflection. An incident ray is parallel to the principal axis. This is the principal axis, and this effective length where it cuts with principal axis is known as optical center. This is the optical center. This is the principal axis we have. Now after that, because it is a converging type of lens, so it will refract such that it cuts the focus. Clear? Now, if I draw the normal in both the situation, where the normal cuts, it always cuts at the center of the curvature. The same we talked about in reflection part as well. In the same concept only, we have in this as well. Now, this is the another ray. If this is the object and we are taking another ray as this, so it will pass straight this way, and this will cut here. This is what the image formation. Now, ray number 1, ray number 1 dash, ray number 2, ray number 2 dash. 2 dash means refracted ray we are talking about. So this is one of the focus of what? If this is the lens part of surface S1, then this will be focus 1, and this will be, we would be having center of curvature as per that as well. Depending on the location of the object, we will talk about in the coming part where would be the image location. So this is S2, then this focus will be S2 of the surface 2, because this is the combination of actually two different spheres, or from the two surfaces of the sphere. Okay, F1 and F2 will be equal if from the optical effective length, F1 and F2 will be equal because you all are talking about class 10th. So for that it would be equal. Okay, so because we are using the identical surfaces S1 and S1 only, SS. Okay, so now let us talk about, we have talked about the law of refraction through a sphere, and which is convex lens. Now let us talk about what is concave lens, then we will see the image formation. Concave lens. So what is a concave lens will be defined by that same pattern only. From the sphere, we are going to cut. This is the part I have cut. Now this cutted part I have drawn this way. Another part I cut. This is the another cutted part. So this part I have taken this way, and they both are from the same sphere. So their radius R will be same. R only, R only. Joining this, what we are getting ultimately, this is the common plane of both bifocal concave lens. How concave lens? From the effective length of the aperture, this is the length. If no, this will not be the length, because this is the plane part. If I separate this, this will be the plane part. You have to be very careful. Okay, so this is the plane surface part, and this is the curved sphere surface part. When wherever the curved sphere part is there, the curvature is there. There we have the aperture, and this will be known as the aperture, the effective length. And from this effective length, as we can see, that it is not bulged out; it is depressed in. The surface is actually depressed in, so that is why it is known as a concave. If it is bulged out, this is the effective length of from the aperture. Now we can see this is bulged out. What is bulged out? The refracting surface S. Again, we can see from the aperture point, from the effective length, if we talk about the surface, refracting surface, that is depressed in, that is why it is known as a concave surface in that situation. Because convex concave are made from, you can make a convex and concave lens from the same sphere, identical sphere only. The surfaces will be sphere, the material will be sphere, shape is even sphere, but the combination will make the difference. And for that combination, we see the effective length from the aperture edges, and whether the refracting surface is depressed in, then it would be concave; bulged out, then it would be convex. What should be bulged out, what should be depressed in, that is what we are talking about, a refracting surface. Okay, so these are the points of aperture, uh, and this is the effective length. And from this effective length, this surface S1 is bulged in. This surface S2, from that effective length of the aperture, is depressed in. This surface is the refracting surface is depressed in. That is why it is a concave lens. So we have developed an understanding of concave lens. Now let us talk about the term. What kind of term we are going to talk about again? Any one of you? We are going to talk about the laws. The first law will be the same. Law of refraction through concave lens. The first law is very clear to us, that the principal axis from where it passes, it always, because principal axis is making 90-degree from the surface. So as we have seen in glass slab, the ray which is normal to the interface, without bending, it moves in a straight line. So okay, principal axis is moving in a straight line, and the point of this joining is known as the optical center. This is optical center O. Now the term comes again. If we have a ray of light, if we have a ray of a light incident such that it passes through an optical center, it moves in a straight line only without deviation. Because when the ray gets refracted from S1 surface, it refracts in such a way that it is again refracted through the S2 surface in such an opposite direction, to get a lateral shifting of the ray, and that lateral shifting is negligible, and ultimately we say it passes in a straight line only, because we take the thickness of the lens to be negligible. Okay, so that is the reason, even with changing with the medium, we assume that the ray is passing without deviation from the optical center only. I'm talking. Okay, so suppose this is the ray. If it is coming from here, if it is passing from optical center, it will go this way only. If the ray is coming this way and this is passing through the optical center, it will move in this way only. So make sure with the law that a ray incident such that it passes through the optical center of the lens, then definitely it will have no deviation in its path. Now let us talk about the second law. The shape and the combination of concave lens is also known as a diverging lens. Diverging lens. Law of refraction through concave lens. This is the law we are talking about. This is the lens I'm taking, and this is the effective length of the entire lens we are talking about. Now, this is the principal axis, and this is the optical center we have. Optical center O. Now, if the ray is coming parallel to the principal axis, in that situation, what happens? In that situation, it will, because it is a diverging lens, so it will diverge itself from its path in such a way, if it is produced back virtually, then it cuts the focus made by this surface only. Okay, so this is focus point 1, and the focus made by this surface will be f2. And if the lens is bifocal identical lens, then f1 and f2 can be written as f only. Focal length f1 and f2, that will also be same. Okay, so this is the ray coming, it will get diverged. This is what the pattern of the ray of a light we have, and here is the intersection and the image is formed here. Okay, so we have calculated few of the patterns of the refraction through the lenses. Let us have a recap about this, and then we will move to the part. If this is the lens, number of incident ray parallel, then what we will have is, there would be a, this is the principal axis, optical center. Always remember one thing: the more you are far from the principal axis, you can see this is the principal axis, and this ray is more aparted from that, more distance is there, more it will show you the divergency. The ray nearby to the principal axis will have less divergency. Always remember this as well. So this is the focus point, and here the concentration is there. This is one pattern. For the same, if I talk about in concave, in this, parallel rays provide you the divergency. Now, the ray which is quite far from the principal axis will have more divergency than the ray which is near. As you can see, these are the diverged rays. The distance, as you will move forward, the distance between the rays will increase. So definitely this is a diverged ray only. This is actually the real rays we are talking about. This is the incident real ray. This is the refracted real ray. Now we virtually see the rays. This is the ray when produced back. This is more diverged ray, and this is less diverged ray. So it is coming this way. This ray is coming this way, and this ray is coming this way. And we found that the image is formed at the focus, and this image will be virtual because the rays intersecting are actually the virtual rays. First law we have talked about. Second law is the rays passing through the optical center does not deviate itself. Optical center. So this is what the pattern we have for concave and convex. This we have gone through. Now we are going to see the trick which I told you. Trick for image formation through convex lens. These were the trick told by me in the reflected ray pattern in the playlist or in the uploaded videos. The reflection 1 and reflection part 2 is given. Go through it, you'll get to know how much is the similarity of this chapter with that. As we talked about concave lens in that chapter, here we have convex lens in this refracted part. Now we have one of the famous lens, that is convex lens, principal axis. Let us see the terminology. This is optical center, focus, focus. If focus and focus it is written, it means that these two surfaces, surface number 1, surface number 2, are of the same radius of curvature. It means the center will be the same. Okay, all symmetrical, both the side, left and right. Now, if an object is, what are the possibilities to put the object? Let us see that as well, and then we will make a table. Now the table is position of object, position of image, then we will add the upcoming terms. Nature of image, size of image. So let us figure out serial number. This is serial number. Now let us see how many possible conditions are there where we can put our object. This is the part of infinity. So we can put our object here also at infinity, one number. After infinity, if we move one step forward, we can put our object at location number 2, which is known as between C and infinity, or you can say beyond C. So we will write those statements in the table part. Serial number 1 at infinity is the object. Serial number 2 beyond C. Serial number 3 after 2 beyond C. If we move one step forward, so we see that we can place the object at location number 3. Then one step forward, we can see that the object can be placed between C and F. One step forward, the object can be placed at focus, and again one step forward, the object can be placed between optical center and the focus. So these are the possible conditions of locating the object. Okay, so position number 3 is at C, and this C is also known as 2F, double of the focal focus, 2F. Okay, at C, or you can say 2F, placed at 2F. Position number 4 between, position number 4 is between 3 and sorry, between C and F, between C and F, or you can say between 2F and F. Now position number 5. If I talk about position number 5, you very well know in position number 5, object is placed at focus. So my object is at focus. So these are the possible conditions of position number 6 says between optical center, and focus. So these are the possible conditions we have talked about for placing, for locating our object. Now let us talk about the image formation. Object at 1 means the object is at infinity. So whatever the ray of a light will be coming, approaching towards the lens, will all be parallel. Why parallel? Because if we produce it back, wherever the coming rays are intersecting, that is the location of the object. But we needed the object to be at infinity, so we needed parallel line to be retraced. Then only the object can be said at that if the object is at infinity. So when the object is placed at infinity, all the rays are coming parallel towards the lens. Now, when the ray of a light are coming parallel, and this is one of the converging lens. So this converging lens, what it does, it makes the image at focus. This is one thing we know. And when it makes the image at focus, then we have a very interesting thing here. The ray, suppose these are the rays coming. I'll erase this after telling you. The number, the name is 1, 2, 3, 4, 5, 6, 7. Now try to see after getting converged to focus, these rays actually are moving up. So rays are actually moving this way. This is ray number 7, 6, 5. And this ray number 1 will go this way. Ray number 2 will go this way. Ray number 3 will go this way. Ray number 1, 2, 3. So as you can see, this pattern of 1, 2, 3, 4, 5, 6, 7 is actually inverted, and this is 1, 2, 3, 4, 5, 6, 7. So at this point, focus F, the image is of point size, but that point is even inverted. This is what the ray of the pattern of the refracted ray is actually telling us. So let me erase this part, as I told you all. I'll erase this part after making your understanding. Now, I have erased this. Optical center. So we get the image, and let me draw the image. This is the image of 1 dash. Dash means refracted. So position of image when the object was at infinity, the position is at F. As the object was moving a step forward, in the same way the image formed after the refraction through the convex lens, the image will also move a step forward. When the object is at this location, then the image will be at 2 dash, and it will be inverted. Okay. And as we know, when we were talking about 1, the real rays were refracted and they were cutting. The real rays are cutting. Okay. So in that case, from the optical center, in that case, bacho, what will happen when the real refracted rays are cutting? The image formed will always be real. Okay. So nature of image real, and the upward from the principal axis, whatever the upward rays are there, they are coming down, and downward is coming up. So real and inverted, you have to write inverted. Okay. Size of image, point size. Again, 1, 2, 3, 4, 5, 6, the steps are clear to you of the location of the object. 1 dash is clear to you. Now where is 2 dash? Step 1, for moving forward, the image will also move forward. 2 dash. Step 3 at C or 2F. Step 3 here. Step 4, 4 dash here. Step 5. Now what is 5? Now as you can see, this is C, beyond C, then at infinity. So this is step 5. Very clear to us? This will very much help you in the numerical part. If the numerical comes of any kind, where you are being given the location of the image, location of the object, or any one of them, few terms are given, you can easily have a picture in your mind that if the object is here, our image should be between this and this, or at that specific location. If the object is beyond C, definitely my image should be between F and C, F and 2F. Now we are very much clear that image should be here. What we will do, we will draw the object, we will draw the image, and then we will join the line. No one will know that whether I have drawn the line first and I have refracted and then intersected, then drawn the image, or first I have drawn the image and then I have retraces the path afterwards. No one will get to know. So this trick will help you in detecting the location of images or the object with respect to image. But while this, you can easily identify what should be the value of V, what should be the value of U, what should be the value of F, like that. That will help, if because if you are specified with the location of the image, then that will help you in solving the numerical. Very, it will make your numerical very easy. I'm sorry. Now let us talk about the step two. So do one thing. As you all can see this script of position of object, take this script, invert this script and paste it in position of image till fifth number. I'm talking, I have not talked about sixth part is a special case. This is the star I've made here. So till fifth, just invert it, you will get the same. Then at C or 2F, then beyond, then at infinity. Same pattern. This is how easily we have seen the five images, and we have easily related one another as well. So we will not get confused and we can easily do this. All will be real and inverted because real refracted ray are coming and intersecting. Now, the special sixth part I will draw for you all. This is the actual position of the object. The object is placed at between O and F. Now let us see the concept. As per the concept, we will get to know the things. Parallel ray to the principal axis always cuts from the focus. This is the ray going on. Again, another ray. Moving from the optical center. And we found a very interesting thing, that this length, normal length between the two rays, was increasing. It means the two rays are divergent rays, which can never intersect after further producing. So we put our eye. We put our eye here at this location. We put our eye. Now, what our eye does, our eye starts receiving these two rays, and as the eye receives these rays, it starts retracing these rays back to get the location of the intersection. And wherever it intersects, we say that is the location of the image. And this is only actually your eye sees. Let me tell you one of the famous example of for this particular position number 6, and that is, this is 6 and this is 6 dash. Clear? So 6 dash will be behind the object, wherever it may be. It is here, it is here, it is after C. It does not matter. The thing is, it is same side of the lens. Okay, in large virtual and same side of the lens. So this will not be real, it will be virtual. For being virtual, we have only one condition. If real reflected rays are cutting, real image, real refracted ray, real image, and virtually produced rays, which are not actually the ray we virtually produced by imaging. That is what virtual rays we are talking about. Virtual and erect. This is virtual and erect. Now see the shape. This is also in symmetrical, it is increasing. Point size After point size, we have step. It will be diminished, not same size. Point size, then smaller size, same size, enlarged size, infinite size. Like that we will have. So point size, then diminished size, then same size, then enlarge, infinite size. Virtual, it will be simply enlarge. Now you are very much familiar with the case 6. That case 6 is actually case 6 will be drawn because it is virtual, so I'm drawing like this. Again, I'm telling this is 6, the virtual 6 dash may be anywhere, okay, at the same side of the lens where 6 object was placed, okay. The condition is behind the object you will get the image. This is one condition. Means at the same side of the lens you will get the image. At the same side where the object is placed you will get the image, but behind the object you will get the image. Wherever the object, the behind the object you will get the image. This is the condition. And where it would be, that is not the condition. It depends on the situation. So this is one of the example of magnifying glass. You are reading the book, you place the book 6 number black in color object between focus and optical center, and you put your eye receives the rays, refracted rays, diverged refracted rays are there, and it retraces back, and the rays which wherever the virtual rays intersect is actually the apparent position of the object. Apparent object means there is no object there, there is actually the image we are talking about, but our eye persists, or our eye says, you can say our eye says that that is the location of the object, that is actually image. So this is what we have image, this is what we have object. So case number 6 is a special case, that is why I draw a star here. Rather than that, we have the very symmetrical and easy pattern. This was the trick for you all. Okay, fine. So till here we are done. In the next part of the video, we will talk about the lens formula, magnification formula, means mathematical point of views. We will study that part of the light in from the mathematical point of view. This is what all theory part and the concept part which you should know, you should visualize in your real world, that too we have discussed. In the next session we will talk about let me write that, we will talk about lens formula, magnification formula, lens formula and its derivation. Magnification and its basic formula, or you can say derivation from the similar triangle we are going to talk about. Third, variety of numericals, and the applied portion, whatever we will come to a conclusion. Okay, so in that second part of the refraction, you will get that. So stay tuned with us in the channel, and definitely we will gain the knowledge, gain the things which are not even mentioned in the books part. So we will grasp the knowledge here in that term. As I already told you, we have a collaboration with one of the senior faculty, Dr. Abhishek Singh. He's a ex-Allen faculty. We will talk about the zoology part in that as well. Okay, so you will get the videos of the NEET, the questions, the theory part in that channel only. That is in the collaboration, as I told you. Okay, so stay tuned. Take care. Bye.
आमन आधार का बंद कर गया
इसको इसको बंद करो